Okay, so segmentation is has been historically a very important and challenging problem in image processing. This task has been pursued from many decades in image processing, and interestingly, it has not been clearly solved by one technique or the other. There are a number of techniques in the literature how to segment regions in images. So we will be discussing some of them. But what is basically segmentation all about? It is the process of dividing an image into separate non-overlapping regions. So an example is shown here. Let us say your image is like this. So you may have to divide your entire image into different regions, R1, R2, R3, R4, R5, and so on. Each region is a separate region which does not overlap with others. And at the end, all the pixels in an image must belong to some region or the other. And then maybe let us say a background. So let us say your image is like this. So these may be all, let us say, your foreground regions, and then at least there is one background region that is also called one region then. So all the regions, all the pixels that way will get categorized into one of the regions. So region can be an object, entire object, or a part of an object, or the background. So there is no clear-cut definition what you call a region, what you call a segmentation. It will depend on problems to problems. An example of segmentation that you would like is shown in this images taken from some image segmentation data set. The goal here is basically to separate images into coherent objects. So this is the ground truth that is available in that data set. So this has been manually, these outlines have been marked based on some coherency. That coherency of the regions can be either similarity in the intensity values or in the texture of the regions, or whether they are part of the same object and so on. So for example, here you can see these, I think, yaks, or I think wild buffaloes. They have been marked as separate regions, and then probably some of the near pixels near in grass, they have been marked in another region. These trees have been marked in another region, and the background sky has been marked as another region, and so on. So this is one possible output. That you cannot say that this is the correct output or this is the wrong output. That different people may see if you give an image to different people, they may perceive different objects in that and different regions. So it's hard to say that this is the correct segmentation of the image. But these are manually done by some people. According to them, they have tried to identify regions in divide this image into regions which are coherent in some sense. So that coherency can be in terms of similarity, in terms of their closeness, in terms of their some texture or any kind of thing. This is another image you can see, and this is the one of the good segmentation results that you would like to be. So another, sometimes this may be difficult to do it really, because people have struggled to get this kind of segmentation output correctly. So another approach that many people have done, instead of dividing your image into one full region or part of a region, you divide your image into superpixels. So it's like a mid-level segmentation rather than a high rather than a full segmentation of image into constituent regions. You do a kind of a mid-level output where you divide some locally close pixels into one regions based on, again, some coherency, based on some similarity, their intensity value or whatever, and you call them as superpixels. So now the idea is, instead of having just raw pixels, this image maybe 1920 by 1080 or whatever size, and working with that level of fine level of things may not always be desired for next level of processing. So going from this to this kind of a superpixel categorization can reduce the number of data points that you need, that your high level algorithm needs to deal with. So this superpixel, this kind of segmentation is also well used. In fact, in one of the deep learning methods, this superpixel segmentation is used as one of the pre-processed input to be applied for further refined object detection and all that. So segmentations can have different uses. can be that basically that depends on application to application and what you want. So the basic principle, as we have said, you can divide. So as I said, there are a number of segmentation algorithms. In fact, the most varied number of techniques that you'll find in image processing computer vision, they deal with segment. They all basically they are in this area of segmentation. So one way we can divide these segmentation algorithms in two categories. Those algorithms which partitions regions based on some kind of similarity. That predefined criteria is there, and that way is one approach. Some of the other approach divide images by identifying discontinuities. So they basically detect boundaries like edges of the regions, and based on those local discontinuities, basically they segment out regions. So the idea of this similarity versus discontinuity is illustrated by this very good example from Gonzalez's book. So let us say we have this image and this which has just one region, probably with some other intensity value. So this has intensity value, let us say I1, and the background intensity value is I2. So the best way in this case to segment out this image is using a similarity feature, because you can see which pixels have similar intensity values. In that way, basically you can categorize it. In that way, basically you can categorize your two different regions, and once you categorize the region, you can also be able to draw the boundary. But another something similar scenario like here, again you can see that this is kind of a similar region which has a similar property, and there is a background region. Now here there is a unique intensity value, background value, but here there is no unique intensity values. It's kind of a textured pattern here. So the similarity here is based on the textured appearance, but there is no single intensity value in this region. So there is some randomness here. So you cannot use similarity here, and or you cannot even do edge detection here probably, because you will get edges response at all the places here, whereas here to do an edge detection was much easier. You could actually do an edge detection. You will get a very clean edge like this, and then once you get an edge like this, so regions which are inside this edge will belong to one region, and our region which is outside this will belong to another region. That is one way. So I think, yeah, so the first image could be very easily be addressed by using a discontinuity based method, where you just do an edge detection, and that way you divide your image into two regions. Whereas in this image you cannot do an edge detection, simple edge detection. So here in fact we can do a similarity based method, and the similarity is again not based on intensity value but some other things. So one way we can use similarities, we can take select a local area in this image anywhere, and find out the variance in that area. Calculate the variance of the intensity values in that region. So now all the regions in the background, they will all have a variance 0 because they all have same intensity values. Whereas all the regions inside this image, they will have a non-zero variance. So in that way you can basically, so now the similarity is based on the variance. A non-zero variance means region 1, and a 0 variance means a background region. So in that way you will end up basically dividing your segmenting out this region. So again you can see here this, if you see here, you are not getting like a smooth boundary but kind of a textured boundary. So the way this image is will be segmented out, you basically divide your image into small blocks, basically small blocks of region, and within each region you basically do a kind of a simple this variance calculation and do basically those things. So some of the boundary, that's why, so you get kind of a textured boundary rather than a blocky boundary here, because these blocks will be created and each block will be categorized as belonging to region 1 or the background region. So I hope this is just a basic illustration In fact, you will not have these kind of simple images for classification. Our segmentation problem will be dealing with much more complicated images, where it's not easy to find out the similarity just based on either just variance or intensity values. But that is the idea. So in, as I said, we have a limited time, so we cannot discuss all the segmentation techniques. So I have chosen to discuss these set of techniques. Of course, the first set of techniques we don't need to discuss, because so that is based on edges. So you first find edges. So you find boundaries between adjacent regions by doing edge detection, and then probably doing some model fitting, half transform, just like what we have been seeing, fitting circles, lines, and all those. And in that way, you can separate out regions from each other. And that we have already discussed in detail. So we are not going to discuss anything more on that. But that is one approach that you can always take. The other approaches are more or less similarity based approach. So one way is you find a good threshold value. So if the intensity values, if the regions can be determined based on their intensity values, then using a simple thresholding based mechanism can also help. So we'll see this in today's class, basically how we can find a good threshold for doing an automatic segmentation. So in the past, we have done manual segmentation using threshold. You manually find out a good threshold value. But now we will try to see some methods where we can automatically find out a good threshold value. Then later on in the next class, we will talk about clustering based. I think we don't have time. So so this also will be discussed in, I think, in the next class only. And class after that, we'll be discussing clustering based mechanisms. So where just using an intensity value may not be sufficient, we may have to use multiple features to identify coherency or similarity between regions. So in that case, simple thresholding based mechanism will not work. We'll have to do some kind of a statistical clustering on pixels which have similar features. So we'll discuss that. Some techniques like k-means, mean shift algorithms, all these are clustering techniques, that how to apply those techniques on image data to do segmentation. And finally, we'll discuss one good set of segmentation techniques for videos. In videos, many times objects are moving. So for video surveillance purpose and all that, we would like to segment out moving objects like vehicles, peoples, from the rest of the scene. So there we can use motion information to identify those regions. So how we'll do that will be the last topic in segmentation. So next 3 or 4 set of lectures, we will discuss all these techniques of segmentations. So in the next class, we are going to talk about what is thresholding. We'll see a simple global thresholding mechanism, and then we'll discuss more optimal thresholding methods, which was presented by Otsu. And this is one of the algorithm which is available in all the image processing libraries, OpenCV or MATLAB, for if you want to find out the good threshold value in an image. And then also some refinement and doing more local thresholding or adaptive thresholding. Any question before we close the session, today's session?
So, can we consider connected component algorithm as, you can say, a segmentation algorithm?
No, connected component generally algorithm is applied after segmentation. So segmentation helps us to distinguish regions. So especially if you are doing with binary segmentation, where we basically have 2 regions, one your background region and your foreground region, or maybe multiple regions. So after you segment out regions, after you identify, okay, this is one region, this is another region, this is third region, and so on. So thresholding, for example, if you want to do a simple thresholding, let us say this intensity values were same, this intensity values were same, and if you apply a thresholding mechanism, what it will give you, basically it will give all ones for all these regions and 0 values for the background region. So this is a segmented output. We call this is a segmented output. Now we have output of segmentation where we have identified, where we have distinguished two different regions and we have marked them with different density values. Now after that, in order to give them different labels, generally that is when CCL algorithm gets used, where we give them different labels generally. Okay, this will get one label, this will get another label, and so on. Yeah, sometime it may happen. Yeah, the segmentation algorithm itself may end up giving different labels. That may happen. In that case, you don't need CCL algorithm separately. But calling CCL algorithm as a segmentation algorithm is not right, because it is not really doing a kind of a discrimination. It is just doing a labeling process. Whereas segmentation algorithm should having a method. It means that we call a method as a segmentation algorithm if it is doing some kind of a criteria for assessing the similarity or distinctness of image regions from one another, and then categorizing them into different regions. So CCL and morphology we'll see are used as post processing. After segmentation is done, then we do connected component labeling, and then we'll do sometimes morphological processing for cleaning up the output. If you remember some of the hand fingerprint images that we had seen earlier during when we discussed morphology. So those were already the output of segmentation. In your original input, your original finger image will be a black and white grayscale image. From that grayscale image, first you have to go to a binary image. And to get from that grayscale image to a binary image, you have to use some kind of a segmentation algorithm, or maybe a thresholding algorithm or whatever. And then after that, you do morphology or CCL or whatever. I hope that is clear. Okay, so today, as we said, we'll start first the simplest approach, which is thresholding based segmentation approach. So in this thresholding based approach, basically we have already seen this very simple approach. We have talked about that. Today we are going, but mostly at that time we would manually select a threshold value. Today we'll can automatically find out a good threshold value using a simple global thresholding method. Another one we'll try using an this simple global thresholding will work only for a very limited scenario. So to get a more optimal method, we'll see Otsu's algorithm, which is the default algorithm method which is available in most of the image processing library for thresholding. And then we'll see that always global thresholding may not work, so we may have to do some kind of a local or adaptive thresholding to take care of some problems. So that is what we will talk in today's class. So basically idea of thresholding is very simple. You see the intensity value, and if you have one threshold, if the intensity value is greater than that threshold, you mark it either one value, and if it is less than threshold, we mark it 0. So mostly thresholding is meant for giving a binary segmented output. Generally, when you have only two regions. Also, you can have multiple thresholds. In that case, you will end up more than binary. So this is an example of just a binary segmentation where you have one region as marked as foreground and another region marked as background. And we have seen those kinds of binary images. But of course, we can, instead of just one single threshold, we can have two threshold value or three threshold value and so on. And then in that way, we can basically divide multiple image into multiple regions. So that is also possible. We'll see that. Talk about thresholding. The general idea is binary segmentation. And good example is being shown here. If you are writing a program for computer to play cards probably, and you give this kind of an image, and this will be a good thresholded image. So it basically tries to find out the card numbers as well as the type of the card using these things. So to do this, we need to have a good threshold value. how can you get this? If you select this, if you somehow get a good threshold value, then getting this results into this results is very simple. It can be done very fast and very efficiently. But the problem is how to decide how to get that threshold value proper, because if threshold is not proper, you can get a very bad result. So if you choose a very low threshold, then most of the regions get marked as 1 and only some of the regions get marked as zeros. So you basically are missing all the card numbers and all that. I don't play cards, so I don't know what all those values are. Okay, and if you set the threshold too high, then basically very few of them, so even these shadow regions of these cards, they also get segmented out as, so you will get these kinds of inappropriate results, which is meaningless results for you. So the thing is, you have to have, it's a challenge to find out a good threshold automatically. And further adding to the challenge, there are many practical problems that add to that channel. One is your basically noise. If you have noise, so like this image, it's very clearly two region image. One is your background and there is your foreground region with a uniform intensity value. So there are just two intensity value, I1 and I2. And if you draw the histogram, you will have just two bins where most of the pixels will be distributed. But if you add a noise, random noise, a Gaussian noise to this image, then if you plot the histogram, you will get this kind of histogram. So now you no more have just one single bin. Your distribution is little bit random, normally distributed around that bin. So this is a Gaussian noise added with a particular sigma, maybe some sigma value. So you can get this kind of things. But if you increase the sigma, if you increase the sigma to a large value, then you get this kind of a noisy image, and the histogram distribution would look like this. So now you can see the problem. In this problem it was very easy. In this problem also it was not so problematic. You can find a good threshold value, which is basically lying at in the valley of these two mountain like distributions. So you can basically choose a midway value between these two peak positions, and probably you will get a good threshold value. But now there is no more two peaks, both the peaks have been merged into one. So now finding out a good threshold value will be almost impossible by any algorithm. So noise is going to be a major problem. Of course, at this point of time, we are not so much worried about noise because we know some methods to reduce noise. So even from this image, if you can get back to this image by doing some kind of a smoothing or some kind of a noise removal methods, then still you will be able to get a good segmentation output. So it's not so difficult to deal with that. But sometimes illumination case cause problem in finding a good threshold value. So you may have a simple image, but if you are taking it with a camera or in a region where there is a change in the illumination from one location to another location. So like here you can see there is a ramp. So if you go from here to here, gradually the intensity is increasing basically from some location to basically from darker to a higher region. So, and this is probably the histogram distribution from, so of this background illumination is shown here, and this is your original image with some noise. But now if there are both factors are there, if there is a variable illumination and noise, then you get this kind of an image. Again, now there is a problem. Now there is no distinct peaks and there is no distinct valley here where you can actually find out a threshold. So again, this will cause a problem in finding out a good threshold. So we'll see how we can address this. So if you know this illumination pattern, probably there may be some way to recover back, go from here to here, from this image back to this image. So if you know this ramp function, how this intensity value is increasing, you can apply a reverse ramp function to the intensity images based on their locations and get back. But most of the time you may not know what is the illumination pattern. It may not be so well defined illumination variation. So how will you deal with that? So we'll see that shortly towards the end of the class. Um, So let us start with a simple method of finding a good threshold value using global properties. And this algorithm is a very simple algorithm, basically kind of a k-means algorithm. If you understand what, if you know what is k-means, it's a very simple, very general, what do you say, a particular case of a k-means algorithm. Later on, we'll see about k-means algorithm being used in segmentation for clustering techniques. But here also, it's the idea is very simple. If you have a distribution of intensity values, let us say, so you initially select an initial estimate for t. You can select any initial estimate from 0 to 255. You can select anywhere, but typically you may start from an average gray level value in the image. So you can find out an average value in the entire image, and that average value may lie somewhere probably here, because you have more number of distributions here and less number of distribution here. So this you may select as an initial threshold value. Now based on this threshold, you divide your intensity values into two groups. So this will belong to one group, let us say group 1, and these intensity values from here to here will belong to another group 2. Now what you can intensity value and maybe a mean of these intensity values in these two groups separately, and then compute a new threshold value which is kind of a midway between the two mean values. So here probably the mean value will be somewhere here probably, and here the mean value may be somewhere here. If you choose the midway value, your new threshold value will basically move towards the actual threshold value, which is the midway between these two peaks. So if you compute a new threshold value, it will be a better estimate of your initial estimate, but still it may not be the best. So you repeat the previous three, four steps, and you keep on iterating it till you find there is no more difference in t, till you a particular value of t. So so you set a minimum value, so and see whether the kth value of the t and k minus 1th value of the t, if the difference between those two is less than some value, then you stop, some delta value, then you stop. So then you converge probably, and most you more all you will converge all at, if the given some conditions, you will always converge in the value between these two bimodal distributions. So this is one mode and this is another mode of distribution. So this works well for finding thresholds when the histogram can be partitioned. So this algorithm will work well if you have a good histogram that we have shown here, where you have one peak here, one distribution somewhere here, another distribution somewhere here. Then this will always give you end up finding a threshold value in between these two. And some examples are shown here. So you can see here. Again, this is a very simple image to clearly the objects have a similar intensity value and the background has similar intensity value. So there are two distinct peaks and some noise and some little bit here and there, but there is a clear distinct peak. And using the global method, you will end up getting the best threshold value, which will binarize this image very well. A little bit more challenging, but still there is a good separation between these two distributions. Again, if you apply that simple global thresholding, you will end up getting a good threshold value, which will binarize your image quite well. But the problem happens when the distributions are not so well separated. They may merge at some point. So in that case, what will happen, even if you choose a threshold value which is kind of lying in between them, like here, still you will end up misclassifying these intensity values as belonging to, these intensity values are actually belonging to class 1, but you will end up classifying in them to class 2. And similarly, these intensity values which actually belong to class 2, you will end up classifying into class 1. So, so the more the distributions basically merge, and they are not if they are not tight, if they are more spread out and they are merging with each other, you will end up basically misclassifying many regions. And in order to do an optimum classification, then you will have to do some kind of optimization techniques by which you basically count the number of pixels misclassified here, the number of pixels misclassified here, and you adjust your threshold value so that that thing is minimized. So if you know these distribution functions P1, P2, in fact, you can write a probabilistic optimization, there some kind of a Bayes optimization strategy and all that is there, by which you can do an optimization to choose a best threshold value, which basically ends up with minimum error of classification. But most of time we will not know these distribution functions because we don't know the regions as it is. So once we know the regions, we can get their PDFs using their histogram, but we don't know a priori what are the regions where they are. So one method which tries to approximate this optimal classification was given by Otsu long back, and it is most of the time it is the method which is used in MATLAB and OpenCV functions. So if in MATLAB, if you use the gray threshold function, it basically implements this Otsu's method. And the idea it basically does is selects the threshold by minimizing the variance within groups. So it calculates the variance of each group and between these two groups. So by trying to minimize the between class variance. So this class is C1, this class is C2. So there is a within class variance of each class, and there is a between class variance. We'll talk about that later on. So by trying to either minimize the within class variance or maximize the between class variance, this algorithm tries to keep each group as tight as possible. So rather than getting each distribution a spread out distribution, it tries to get each distribution a tight distribution. And when you do it, when you end up making your group tight, and be minimizing their overlap, and in that way you will be minimizing the misclassification. So that is the idea. If you can classify your intensity values or your pixel distributions into groups which are as tight as possible, then you will basically be getting the best possible thresholding. Again, this algorithm will also work only when histograms are basically bimodal and they have uniform illumination. If the illumination itself is non-uniform, you will end up not getting good threshold value. And first we'll talk about only bimodal. Of course, these algorithms can be extended to work for multiple peaks, for multiple distributions. But right now we'll assume only there are two distributions. An example of an image is shown here. So you can see the buildings, most of the buildings, brick structures and other things, they have similar intensity value, and the background uniform background, and this some portion of the building they have another distribution. So this will end up give a threshold. Also will give a threshold value which will binarize the image like this. Of course, this may not be an ideal binarization if you want to segment out this entire building into one category, but it makes sense that this intensity value here and this intensity value here are more closer than the intensity value of these portions here. What basically, any question till this point? Anybody wants any clarification before we discuss the mathematics of Otsu?
Excuse me, sir.
Yes, Gaurav.
Yes, sir. So as you mentioned that even in like the for any thresholding based method, we expect that there are like two distinct distributions present within the image. Now, such a scenario can be said to be possible if we like take the image most probably in its original form. What I mean to say over here is that, say for instance, if you initially apply histogram equalization technique or something similar, then in that scenario, our entire histogram like gets even, and in that case, it will be very difficult to distinguish in between the two probability distribution functions. So, sir, can I say that applying histogram equalization technique or some other transformation technique can hamper this segmentation process?
Yes, yes, it will. Your observation is quite correct. That if you try to use a histogram equalization and all that things, it can hamper your segmentation process itself. So because smoothing and all those things are basically trying to basically smoothen out your distribution rather than make them very distinct. So and similarly histogram equalization also can tend to spread out your distribution. Those can work against your good segmentation. So yeah, so depending on what you want to do, you will have to choose your pre-processing methods carefully. So all pre-processing methods cannot be applied for everything. So if you have to segment out your image for some higher level analysis, then probably you should not do a lot of smoothing or histogram equalization. So
Okay, sir.
I
Okay.
agree with you. So in Otsu's method, basically, um, so what we said basically, it tries to make each mode of distribution or each mode of distribution as tight as possible. So one way is you calculate the within class variance. So for each class, you calculate its variance, within class variance. We are calling it within class because we'll talk about between class later on. But variance is normally within class only. So for each class, you calculate its variance and weight it by its mass, or it's basically the number of pixels belonging to that variance, and sum both of them. Then you get this weighted within class variance. So this weighted within class variance is basically the sum of the two class variance weighted by the number of pixels belonging to each class. So q1 q2, if you can see here, is nothing but the number of pixels from 0 to t and from t plus 1 to the last, whatever is the last value. So here probably 255 or whatever. So if you have a if you are using a t value somewhere here, basically, so these all pixels you count here will be q1t, and another these pixels will belong to q2t. So, and how do you calculate mean and variance? The same formula. So their intensity value multiplied by their uh, the number of pixels of that intensity value, and you sum this for all the pixels and divided by the total number of pixels. So that gives you mean. And similarly, variance is the difference from the mean, square difference from the mean. So I think these are the standard statistical formula. So you have to calculate, basically, finally you have to calculate each class variance and weight it by the number of pixels belonging to each class, and that gives you the weighted within class variance. And you will have to basically now, you will have to minimize this. So you'll have to find the value of t which minimizes this. So what you have to do, you have to start with 0 pixel with t as 0, threshold from 0, and calculate this value. Then go to the next value of t and find out this, and go to next value. So you have to start from 0, go up to 255 and store all these values here, and the one which gives you the minimum value, that will be your threshold value. So that is the idea. Basically, you run through the full range of t from 0 to 255 and pick that value which minimizes this your within class variance. But doing this is going to be a little bit slow in terms of computation, because every time you have to do all these calculations for all locations, it can be a little slow. So there is a trick he used, basically, he exploited the relationship between within class and between class variance, because by that we can end up writing a recursive function which can do a faster calculation. So we'll see how, basically. So what is between class variance? between class variance is defined as the sum of weighted square distance between the class means and the global mean. So the global mean is basically the actual image mean. So you have the image, the actual image pixels. If you don't consider any distribution, any class 1, or class 2 or something, take all the intensity values of the image and find the mean of the image. That is your global mean. So if you have two distribution, let us say here, global mean may be somewhere, let us say here, and each mean will be here. So the between class variance will be the sum of weighted square distance between the each class mean. This is mu1, mu2, and this is the global mean, let us say, or mu I here. Basically I should have do the same. So it basically, that is what it is calling as between class variance. Again we have to weight it, because so that if one of the distribution has most of the pixels, otherwise it will dominate it. So we'll have to weight it by the distributions. And now the total variance of the image, the total variance is again taking the image it is and finding its variance in that image. That is going to be the sum of the within class variance and the between class variance. So the variance that is within the class, each class, and all that is between the class, if you add up all those variations, that will give you the total variance in the image. Now this total variance is irrespective, is not a function of t. This is not a function of t, not a function of your threshold value, because this the image variance is going to be the same irrespective of what t value you choose as a threshold. So now so trying to minimize this within class variance is same as maximizing this between class variance. So instead of what we were trying in earlier, we were trying to minimize this, but to minimize this we'll have to calculate all these values, the equations that we have seen this. But instead of minimizing this, if we try to maximize this, why? Because this is a constant quantity, so you have to so you can to maximize this between class variance, and this between class variance after some linear algebra can be written, after some simplification it can be written as this expression. So you can see how this expression comes from the book. I've just used the final result. Now to maximize this quantity, you can see this is a more simpler equation, and this can be written in a recursive fashion. Because how you can start with t is equal to 0, initialize t is equal to 0. So q1 0 will be just the number of pixel values in the intensity bin 0, that is your p0. Mean mu1 0 will be just 0 itself, because that is the first class, and all of the other remaining intensity values belong to the second class. So the second class, the mean you will calculate like this, which is the same mean formula basically. So except the pixels in the intensity bin 0, all the remaining pixels, and this is in the numerator basically. So you can initialize, so you need three values, q1t, mu1t, and mu2t. So for 0 it is simple. Now you can use a recursion to get the next values of q1t, mu1t, and mu2t. How? Q1t plus 1 is nothing but the number of pixels till t plus the next, in the next bin how many pixels are there, t plus 1th bin how many pixels are there. If you add that will give you the number of pixels belonging to class 1 at intensity value t plus 1. And how do you update your mean for the class 1? So it will be the previous mean that you have calculated up to t multiplied by the number of pixels till t. Then you have to also take into account so it's like a running average that you are doing. Now the next intensity value is your t plus 1 multiplied having that intensity value divided by the total number of pixels till t plus 1 that you have already calculated here. So that will update your mean for class 1. And similarly, mean for class 2 can also be updated similarly using the values that you have calculated here. So you can understand this equation also. This is the global mean, which is always constant, and minus this one and subtracted this. So for the second class, you will get the mean by this. So this way you can write a recursive function, and the computation number of computations will get reduced. It will be much faster. It will converge much faster. Still, you will be doing for all 0 to the last 255, and you will be ending up picking the t value which maximizes this value. But this implementation will be little faster. So what is the result? Anybody wants any clarification here? I was little fast, I think, but I think this is simple algorithm and mathematics here, rearrangement of equations. I hope if anybody wants me to go over it again, I can do it. So the result of applying this Otsu's algorithm, so on this image, I don't know what this image is all about, but I think probably some biomedical image with some cells or something. This is the histogram. This does not look like a good histogram. So if you use a simple global thresholding that we do it basically iteratively finding the two, you may not end up into a good threshold value, and the result can be disastrous here. You are not getting a good threshold value with a normal or the first method that we saw. But with Otsu algorithm, it somehow ends up finding a good threshold value, which basically segments out probably these regions, and it categorizes groups this region and the background into one, and I think this region is categorized something else. So I think we'll have to understand what this all image is all about and what we are trying to segment out in order to understand the result much better. But somehow it ends up getting a better result in terms of segmentation than this results, because for the same reason, in global thresholding we are just doing an averaging, and we are not exhaustively searching all search space. In Otsus, we are basically exhaustive searching from all locations from 0 to 255, whichever is giving the best. Here we are basically estimating some value and then again doing a convergence, and it may not converge to minima, global minima. So if you have an optimization function, it can have many minimas, so it may not always end up into a global minima, it can end up into a local minima, so that you can think of like that. So your simple averaging that you were doing in the first method was not like an exhaustive search, so you may not end up into a very an optimum threshold value. But in this, you are doing an exhaustive search for all possible values of thresholds and finding out the best pick, so you can expect to have a better output. Of course, you can extend it if you have more than two distributions. If you have, let us say, 3 distributions here, class 1, class 2, class 3, then you will have to you can extend it also. So now we will, instead of 2 classes, now we'll have a in case of k classes, we'll basically have now 2 thresholds. Instead of 1 threshold, we'll have to find out 2 thresholds, and the method will be the same. We'll have to maximize the between class variances for the pair of, so we'll take 2 pairs together, t1 t2 values together, and using these t1 t2 values, we'll have to calculate the between class variances, and we have to do an exhaustive search for all possible pairs of t1 and t2. Of course, it is going to become more expensive, more exhaustive. The computation will increase. So beyond 3, Otsus is never used. You can use Otsus up to 3 classes. Beyond 3, it will not give. It will be slow and it will not give a better result. We will see some more advanced techniques in the coming classes when we have to do that. Clustering is a much better option to do that. So this is an example of a Otsu's dual threshold, which is extended to 3 cases in 3 regions. So now here there is 1 region here, second region here, third region here. So you can use the same Otsu's algorithm, dual threshold algorithm, to find out these 2 values, and you end up getting a good threshold. So now we referred to this problem of illumination. We talked about this illumination problem. Even where you have illumination, that will also disturb your distribution, and in that case, even if you apply a good reasonable algorithm, you will fail. It will upset your thresholding. So an example is shown here, and you may not know what is the illumination, what is the variable illumination. It may not have a it may not have be clearly defined or known beforehand. So methods to deal with that is one kind of an adaptive threshold. So instead of a single threshold, instead of single one threshold, global threshold for the entire image, we can divide an image into sub images and threshold those sub images individually. And this method is called adaptive because instead of using a global thing, we are now using each pixel, the threshold value for each pixel will depend on its location. So an idea is here, you have this image, if you can divide into, let us say, 2 by 3 grid. Now for each grid, basically the distribution, if you try to see the distribution, you will have this distribution, and within each local region, probably because the illumination was such that it was not so drastic. So within a certain region, the illumination was not changing so drastically. So the distribution did not got affected in a local region or in a sub image of this entire image. So now within each you can apply this Otsu's algorithm or a simple thresholding to get the clear peak good threshold value, and using that you do a threshold for each. And this is the result of multiple of doing thresholding in each region independently. So in that case, even with a variable illumination, you may end up getting a good output. You can extend it to instead of dividing it into grid, you can do it like a moving average, like filtering, the way we were doing filtering basically. So that is what is called local processing. So you have an image, you define a neighborhood around each location, each pixels, and within that neighborhood you calculate some properties of that region, and based on that you decide the threshold, and then move this region to the next location and decide it for the next pixel, and so on. So, and in that case, now you don't need to just rely on the intensity value. You can take some local properties like the mean in that neighborhood, the variance in that neighborhood, and you can also have a flexibility to define some kind of a logical predicate. Okay, that only if the intensity value is greater than some a times the variance and b times the mean, then only I will say, okay, this belongs to the region 1, otherwise it belongs to region 0, background or the foreground. So in that way, we can do some more, we'll have some more power on thresholding doing that. So I don't have a result of these things, but one result I have this using moving average here. One application of this can be, for example, when you take image from your phone. So sometimes because of your camera being focused on a particular spot, or due to some kind of a maybe lightning, your camera may flash or something. There is a variable illumination that you get, and that variable illumination may end up. So if you use a simple global threshold using also something like this, for you end up getting this kind of a result. But if you use this local thresholding in each region separately and do a moving average, you end up you can get a proper result. So this is an example from book. There may be some more details how you do this moving average, exactly how you define your predicate for this example. But I can think even if within the same region, if you do this global threshold, a simple so just like adaptive thresholding, we were using an Otsu's method within each sub image, you can do that. Or if you want to simplify, you can use the mean and variance in that neighborhood and build a logic based on the mean and variance to decide that. So this is what is there. So this content was from the Mozalvi's book itself. So we have discussed simple thresholding based techniques. We saw the basic global and Otsu's global thresholding, and then we saw some adaptive and local thresholding methods. Next lecture we'll be talking about clustering based segmentation methods, which is more general methods which include this thresholding and all that. So we'll talk about k-means and mean shift algorithm for segmentation in the next class. Today I think we have time, but I think we can take 1 or 2 questions and stop today's class. Anybody would like to